Yep.
Okay. Okay, so we don't have to worry about a sub x really, because the way we design the instrument, there is no net DC. So our net DC equals 0. Hence U equals 0. Hence A equals 0. That's why the first thing I never understand is why people make a big deal out of A. A equals 0. End of story. Now, the question then is, what's this second value, Q? Well, when I ask you, when you want to talk about Q, your answer is Q is a calculated number. Okay.
I'm sorry, what does Q represent physically?
That's what we're going to get to. So first, it's a calculated number. It's got the mass to charge ratio inverted. Okay. These are the parameters of the trap that you can't change. What you can change is the voltage of the RF. Okay.
So that's the amplitude of the RF.
The amplitude of the RF peak to peak. So, for a known mass, in a particular setting of the voltage, you calculate the Q value.
That's a trapping potential?
It's not a trapping potential, it's a Q value. It's just a calculated number.
Is that the Q thing you said? 0.25?
Yes, that's the same thing. Okay, now, A equals 0. That's all you got to know. Because I don't even try to understand A because it always equals 0 on a commercial trap. Okay.
So Q, what does Q physically represent?
Now that's the interesting question. So what the Q allows us to do is to build this picture. Okay. So this is the linear trap stability diagram. Okay. Unlike our previous trap, it is completely symmetric. Okay. It is basically a quad picture with a bottom and top half. Okay. What we're plotting is Q versus A. And what does A always equal? 0. So the ions don't sit on a plane, they sit on the A equals 0 operating line.
I missed the...
You haven't missed what Q is yet? No. Okay. Now, so we take each mass with one voltage set on the RF, and we calculate the Q value, and we put the ions on the picture at different locations. Now, the question is, what does Q physically manifest itself as? Well, the key to understanding that is to realize that Q intersects these other lines. Okay? You have isobeta X lines and isobeta Y lines. And notice that the lines intersect each other at the same point on the Q. So an X line intersects a Y line at the same point. So whatever the isobeta tells us, it tells us the same for the X direction and the same for the Y, because the trap is perfectly symmetric.
So these numbers represent voltages?
No. What they represent is the ability to solve the isobeta equation, which gets us the frequency of the ion. So these isobeta, and there's an infinite number. I've only drawn in a few of them, but there's an infinite number. So what happens is you find the Q value of the ion, you put them on the picture, and then you find what isobeta line he intersects. So let's say this guy intersects an isobeta line of 0.4. From the isobeta equation, we can calculate the frequency of motion of that ion. Okay. Now, remember what I told you when we were on the longitudinal curve page. What did I say about every M over Z in the trap?
Depends on charge state.
They have different frequencies. Every M over Z moves at a different frequency. Well, here's why. Because every M over Z intersects a different isobeta line, hence having a different frequency of motion. Does that make sense?
Obviously, it depends on mass.
It depends upon, you're right, so each mass has a different frequency. Those frequencies can change. How do we change an ion's Q value?
By giving a kinetic.
By changing the voltage of the RF, the quadrupolar voltage. By changing the amplitude of the RF, the ions move up or they move down. Okay? Hence they change frequency. Does that make sense? Yes or no? This got to make complete sense. You got to understand this.
So this is a way of visualizing the frequency as dependent on the amplitude RF.
Right. Right. That's all it is a way of linking frequency.
Areas of stability, and I would guess unstable means ejected.
Right. Now, you'll notice there's different regions. X unstable, X and Y, Y, and Y, or X. When an ion becomes unstable, it hits the surface. Okay? So when an ion's over here, it hits the X rods. When it's over here, it hits the Y rods. When it's over here, it can hit either the X or Y rod with equal chance. It's going to go to one rod, it's going to whack one of them. Does that make sense? So we want to avoid this region right here. All this stuff outside we want to avoid. Does that make sense? Because we don't want the ions to hit rods or you don't see them. Okay, now, an ion cannot hit 0, 0. There's no way for an ion to have a Q of 0. So this side is never reached. This side is a real value. There's a limit at a Q of 0.908. At a Q of 0.908, the ions are no longer contained by the RF field. Basically, they're moving at too high of a frequency to go out of sync, and they go whoop, and they whack a rod. They just kind of spin uncontrollably out, and they whack a rod, and we lose them. So we want to avoid this region right here. So what we do is we drill a hole at the little red asterisk. And we drill that hole via X-rod resonance ejection. Okay.
These lines means the motion.
These lines right here, those are the isobeta lines. They tell you the frequency of the ion's motion.
This is a theoretical calculated by our equation.
Right. Exactly. There's another equation which I've never thought to display on my slide. It's kind of boring. But you can calculate the frequency. Okay. Does that make sense? Okay, now.
What is this? Do the red thing again. So what is
okay, now. We can't come right here because the ions experience instability and they whack a rod. So we're going to eject them earlier by making the red asterisk. Okay, so the red asterisk is going to be the point at which we eject them. What does the red asterisk represent physically? I'm not saying how we do it. What does it represent? What is the ejection point? Is it a power? Is it a? It's a frequency, is what it is. Okay. It's a frequency.
It's a movement.
Okay, don't ask how we do it yet. It's a frequency. So what happens is which ion is closest in frequency of my 3 ions displayed? The orange. How do I take this orange ion and change his frequency to match the red asterisk frequency?
It's Tacoma Narrows Bridge, right? You resonated out.
No. Easy. How do we change this ion's Q value? What do I adjust?
Voltage.
The voltage, what kind of voltage? The quadrupolar voltage on the RF rods. So I up the quadrupolar voltage and he walks along the line. Now, is he physically moving anywhere? No. He's still doing the same Z motion he was doing before, but now his X motion has a higher frequency. So each step he takes, he increases his X motion frequency. Eventually he'll approach the red asterisk. At the same time, the green ion will move to about here. And the blue ion will move to about here. Does that make sense? And what was I adjusting to change his frequency?
The amplitude of the RF.
Amplitude of the quadrupolar RF field. Everyone say that out loud. The amplitude of the quadrupolar RF field. You got to put the whole sentence there because in another minute you're going to have a whole other RF field on top. So it's the quadrupolar. Quadrupolar means applied to 4 rods. Okay. Okay, now, how do I create the asterisk? Okay. What I do is, I apply a second RF voltage to the X rods only. Okay. It's an AC, it's an alternating current, which is just another name for RF. Okay. At the frequency of the red asterisk. Okay. Now, this is not a quadrupolar, this is a dipolar, but it only happens on 2 rods. Okay. Quadrupolars change what? What does the quadrupolar set for the ion? What does it determine about the ion? If I know the quadrupolar amplitude, what can I know about the iron?
The frequency.
The frequency. Quadrupolar does frequencies. Dipolar moves ions. Put your hands up. Okay. X rod, X rod. Now, the dipolar